This is chapter 12, and section 4 is about the properties of alkanes. Like any compounds, the chemical and physical properties of alkanes depend on their molecular structure. So, for example, the properties of solid alkanes make them suitable to act as coatings on fruits and vegetables to help retain moisture, inhibit mold, and generally enhance their appearance. This is because of their molecular structure. One of the most obvious properties of an alkane is its physical state. Is it a solid, liquid, or a gas? This physical state is also going to be a key factor in determining what we can use the alkane for. So for example, for the smaller alkanes with between 1 and 4 carbons, in other words methane, ethane, propane, and butane, these are all gases at room temperature, and they're widely used as heating fuels from compressed tanks. Alkanes with 5 to 8 carbons, pentane, hexane, heptane, and octane, tend to be liquids at room temperature, although they're relatively volatile, meaning they have low boiling points and can evaporate relatively easily. But still, these are useful as fuels. In fact, octane is the primary component of gasoline. Alkanes that have between 9 and 17 carbons in a chain tend to be liquids with higher boiling points at room temperature. And they're found in motor oils, mineral oil, kerosene, diesel, and jet fuels. These are thicker liquids, higher viscosity liquids. They don't flow as easily. Alkanes with 18 or more carbon atoms in them are known as paraffins, and these are waxy solids at room temperature. They're solids, but they're not rock solids like we would think of for an inorganic compound like a salt. They're soft and they're pliable. So for example, petroleum jelly or Vaseline is a semi-solid mixture of hydrocarbons with more than 25 carbons in them. All of these properties and states of matter that we just discussed are due to the melting and boiling points of the alkane. Remember that alkanes only contain nonpolar bonds. They have nonpolar carbon-carbon bonds and pretty much nonpolar carbon-hydrogen bonds. This means that the only forces holding one alkane molecule to another are weak dispersion forces. These are very easy to disrupt, leading to low melting and boiling points for these things. The other thing to know about dispersion forces, though, is that they increase with the surface area. The more surface area there is for two molecules to come into contact, the more chance there is for these dispersion forces to work. And so what that means is that the larger a molecule is, or the more surface area it has, the stronger the forces holding it together will be. That's going to make it harder to pull apart and increase the melting and boiling points. So here we can see the boiling point increases as you go from methane, which is 1 carbon and has a boiling point of negative 164 degrees Celsius, to ethane, which is 2 carbons long, and its boiling point is negative 89. Propane is 3 carbons, and it goes up to negative 42. Butane is 4 carbons long, and it finally gets to positive Celsius temperatures, 0.5 degrees Celsius. And pentane is 36 degrees Celsius. The boiling point is just below human body temperature. But in addition to extending a carbon chain, we can also reshape a carbon chain by forming an isomer. So if we look at how branched alkanes are different from straight chain alkanes, what we find is that the branched alkanes tend to be more compact than a straight chain alkane with the same number of carbons. So in other words, a molecule like hexane, which is 6 carbons in a row, is more extended or has a larger surface area than something like 3-methylpentane, which is a 5-carbon chain with 1 extra carbon substituent. It's still 6 carbons. In fact, these are structural isomers of one another. But 3-methylpentane is a little bit more compact due to this branching point here, and so it has a slightly lower boiling point than hexane. If we introduce another branching point so that we have 2, the molecule becomes even more compact and the boiling point decreases a little bit more. So the more branching points you introduce into a carbon chain, the lower the boiling point will be. And this is because it's making the molecule more compact and reducing the surface area for contact between two molecules. You might think that cycloalkanes are even more compact, and so they'd have even lower boiling points. But in fact, that's not the case. In cycloalkanes, the carbon-carbon bonds have limited rotation due to the rigidity of the ring structure. They also have a relatively larger surface area compared to the branched counterparts. Whereas the branch counterparts are compact into more of a spherical shape, cycloalkanes are compacted into an almost plate-like shape, a flat plate. This gives them more surface area for the dispersion forces to act, and it also allows them to stack more closely together, which, combined with their rigidity and their limited rotation, makes them stick together pretty well. In fact, the cycloalkanes have higher boiling points even than the straight chain alkanes with the same number of carbon atoms. You can see how that works in this chart. The parent compound, pentane, the straight chain alkane, has 5 carbons and a boiling point of 36 degrees Celsius. The structural isomer with 1 branching point has a slightly lower boiling point of 28. The isomer with 2 branches has a lower boiling point of 10 degrees Celsius. But the cycloalkane, where the chain is looped back on itself and forms a rigid closed ring, has a higher boiling point even than the original pentane. It has a boiling point of 49 degrees Celsius. We've seen combustion a few times in this course already, so I'm not going to spend too much time on it here, except to note that virtually every organic compound is flammable and can burn in the presence of oxygen to produce CO2 and H2O. Here we can see 2 examples of combustion of typical alkanes. The first is methane, CH4, which is actually natural gas that you might use in your home to cook or heat. And the second one is propane, C3H8. This is used more for portable heaters or gas barbecues for grills. Like most organic compounds, alkanes are pretty much insoluble in water because they're very nonpolar. They're also less dense than water because the carbon and hydrogen that makes them up has less mass than the oxygen that's a primary part of water. So if there's an oil spill in the ocean, for instance, you'll see the oil, which is made up of a lot of alkanes and other organic compounds, float on the surface as a thin layer instead of sinking to the bottom. The alkanes in the crude oil don't mix with the water because of the difference in polarity, but the reason that they go to the top rather than sink to the bottom is because of the density. So we've balanced a lot of combustion equations before, but let's just do one more example like that to close out this section. Butane, C4H10, is a fuel often used in lighters. Write a balance equation for the complete combustion of butane. So we begin with the formula for butane, which is C4H10. And we know that because this is one of the smaller alkanes with only 4 carbons, this is going to be a gas at room temperature because it has a very low boiling point. Combustion means combining this with some number of oxygen molecules, oxygen also being a gas. And this is going to create some number of CO2 molecules, also a gas, and some number of water molecules, which in this case are usually also in the gaseous state. We don't have to worry about writing in the energy. Generally, we know that combustion reactions produce a lot of energy. So now we just go through and balance this. Since we have 4 carbons from the butane, we would start with 4 in front of the carbon dioxide. Since we have 10 hydrogens in the butane, we're going to want to put a 5 in front here so that we can get 10 hydrogens from our 5 water molecules. However, that's going to give us 8 oxygens over here plus 5 oxygens over here, which is going to be a total of 13 oxygens. This is an odd number of oxygen atoms which can't really come out of oxygen molecules which are paired up. So what we have to do is go back and multiply everything by 2. This would be 2, this 4 would become an 8, this 5 would become a 10, and then we have to look at how many oxygens we have to figure out the oxygen coefficient. So here we have 8 molecules of CO2, 2 oxygens each, that's 16 oxygens here, plus 10 oxygens from the water molecules, gives me a total of 26 oxygens on the right-hand side. To get 26 oxygens from pairs, we need to take 13 pairs, or 13 oxygen molecules. And then that gives us 26 oxygens on the left-hand side, 8 carbons, 20 hydrogens on both sides.